Let's find a moment of inertia about an axis passing through the center of mass of this rod, which has a uniform density. So we know that the center of mass is in the middle of the rod. And a moment of inertia about this z-axis, which points outside the screen, is equal to the integral of the square of the radial distance from each element of mass to this axis with respect to the mass. So dm in this case is the density by the cross-sectional area of the rod multiplied by the thickness of that differential element. And we divide this over the total mass of the rod to get an expression for the moment of inertia in terms of the mass, which is density by area by length. Then doing some cancellations, we can write the differential mass as follows. And then we can replace r with x, where we're integrating with respect to x. And here we integrate from minus L on 2 to L on 2. And evaluating this integral, you should get ml squared on 12. Let's find a moment of inertia of a thin rod with a non-uniform density about an axis passing through point O. So recalling the definition for the moment of inertia, which we'll write in terms of the x variable, where x is the distance to an element of mass, dm. So again we can write the differential mass element using the linear density by dx. And then substituting for dm and lambda, we obtain the following expression. And we integrate from 0 to L. And if you evaluate this integral, you'll get the following result. Now we can write this in terms of the mass by integrating the density function with respect to x from 0 to L. And if you evaluate this integral, you get the following expression. So we can write L cubed in terms of the mass. And then substituting for L cubed, we get 3/5 m by L squared. Let's find the moment of inertia of a thin ring with a radius r about its axis, which points out of the plane. So recalling the definition for the moment of inertia, so in this case we can choose our differential mass element as some slice of that ring. So this angle is d theta. So we can write a differential mass as the linear density by r d theta, and divide this by the total mass, which is a linear density by 2 pi r. And if we make some cancellations and multiply through by m, we can write dm in terms of the mass. And integrate from theta equals 0 to theta equals 2 pi. So we recognize that the radius is constant, and therefore we can take all the constants outside the integral. So therefore the moment of inertia evaluates to mr squared. Let's find the moment of inertia of this disk, which has a radius r about its axis, which is perpendicular to the plane. So using the definition of the moment of inertia, where we break up this disk into infinitely thin rings. And the radial distance of that ring from the center is r, and the thickness of the ring is dr. So therefore the area of that ring is 2 pi r dr, and then multiplying that by the areal density gives us a differential mass. And then dividing through by the total mass, which is the areal density by the area of the disk, and doing some cancellations, we can now write dm as follows. So this becomes r cubed, and taking the constant outside the integral, and integrating from r equals 0 to r, the moment of inertia evaluates to mr squared on 2. Let's find the moment of inertia of this annular ring about its axes, which points in a z direction. So what we do is break this up into infinitely thin rings with a distance of r from the center and a thickness of dr. And the moment of inertia is defined as follows. Therefore dm is the areal density by the area of that ring, which is the circumference by the thickness. And we'll divide by m to write dm in terms of m. So m is equal to the areal density by the area of the annular ring. And after doing some cancellations and multiplying through by m, we can substitute for dm. And we integrate from r0 to r. And now you can do some simplification. Take the constants outside the integral, and then evaluate the integral and post your answer in the comments. Let's find the moment of inertia of this cylinder about its axes, which passes through the center of mass. So designating the radius as r, and the radial distance to this infinitely thin ring as r, and giving this ring a thickness dr, and the moment of inertia is defined as follows. So in this case we'll break the cylinder into infinitely thin shells, and these shells have a volume of 2 pi r by dr, and that's multiplied by the length of the cylinder. And multiplying the density gives us the differential mass. And then dividing by the mass of the cylinder, well, that's equal to the density by the volume of the cylinder. And now we can do some cancellations. Substitute for dm. And then integrate from 0 to r. And if you make some simplifications, so that will be r cubed, then taking the constants outside the integral, and then evaluating this integral, you get the following moment of inertia.